Thank you very much for the nice introduction, and thank you for having invited me here. So as I said, exactly, I'm staying for 3 days, but I want to make the most out of it by spending time with you and asking all the, answering the questions you might have. So please do not hesitate to ask questions, because graduate school lectures can be boring unless there is some kind of interaction with the students. So no questions is silly, so please do feel free to ask at any point. Okay, so I'm going to talk about global PDF fits connecting low to high energy physics, and we're going to have 5 lectures. Clearly, so what I want to do is I want to give an overview of our current understanding of the structure of the proton. I will focus mostly on the proton. I know you heard about the other nuclei, but I'm going to focus on that because there is already a wealth of material to talk about. And I want really to go from the basics, from the Feynman parton model is in the 60s to the modern QCD picture and how we understand it. So I will introduce some basic concepts and techniques behind this global fit of the functions that parameterize the structure of the proton. And this is something that we will go in depth, especially tomorrow. So again, tomorrow might be a bit more technical, but if you ask questions, it's going to be interesting. And it's beautiful because there are lots of ingredients involved, from high energy to low energy physics. So we have all the non-perturbative effects, perturbative QCD, experimental measurement. We need to understand a lot about statistics and interesting mathematical problems, and as well as higher order theoretical prediction, phenomenological tools, and machine learning. So we'll try to cover all these ingredients that we have whenever we talk about global fits of the proton structure. And then I will mostly discuss PDF-related phenomenology, mostly at the LHC, but I will also talk about the EIC, and then some of the current frontiers and challenges. Okay, so again, I can just give a kind of my own personal view on the topic. So 5 lectures seem to be a lot, but actually I have to choose what to cover. And hopefully there is some flexibility depending on what you're more interested in. Okay, very good. Here I put on the slide some of the references that you can look at. The ones that are not available, maybe these notes that are the basic of what I'm going to write on the board later on, is something that I can post on the Slack channel, so you can all have a look at it. And these are very nice reviews that have been written in the past 10 years about PDFs. So you can see everything I tell you from different perspectives as well. Okay, very good. So today I will start from a kind of aerial view, from a kind of motivation. So why we care so much about the structure of the proton, what are the ingredients that enter theoretical predictions. And then I will go at the basic, like talking about the parton model and how it is modified whenever you start introducing quantum chromodynamics and corrections. And then I will finish with collinear factorization. Who of you has heard about collinear factorization? 1, 2, okay. 3, 4, some, okay, good. So I will, hopefully by the end of these 2 hours, it's going to be clear what it is and why we rely on that for many of the theoretical predictions we do. Okay, very good. And then tomorrow we'll go through other stuff, but I will tell you tomorrow. Okay, so as you all know, we have this beautiful model of particle physics, which is the standard model, which is really one of the greatest triumphs of quantum field theories in the past century. And it's really a remarkably successful theory, has been tested to the extreme limits, and so far we haven't yet a convincing deviation from the theoretical prediction of the standard model, which can be frustrating for some, but it's also very exciting for others. So, and I think the truth is somewhere in the middle. Very good. But we know, on the other hand, that it is necessarily incomplete. So there must be something beyond, some phenomena that the standard model cannot describe. And this is something that I want to mention in the very last lecture when we look beyond what we have. So somehow we are at a point where there is some physics beyond the standard model, but the effect has to be found either in some extreme phenomena or in some very, very high energy phenomena that causes some small deviations. So you really need precision physics, or you need in some really weakly interacting kind of phenomena that again needs a lot of precision. So the name of the game, somehow nature instead of showing some huge deviation at the very beginning, is putting us into a kind of different game than what people were expecting at the beginning. We haven't found any new particles yet, but we have been given at the same time the tools to go much deeper in what we see, to a level of precision that I'm going to show you was never reached before. So we can see with the lens of precision and see the little deviations that nature wants to show us, okay? Very good. And I think that we have a huge opportunity, which is given by the colliders, because we really have a unique opportunity to test our theoretical predictions from the standard model or from theories beyond the standard model experimentally in a controllable environment. And so you need things from the theory point of view. So you need, again, we normally use quantum field theories to write down our Lagrangian, starting from a model, so standard model, supersymmetry, extra dimensions, composite Higgs, anything you like. And from that, you give a prediction for the cross sections. And then on the other hand, we have the measurement of the properties of the physical objects that are produced at these colliders. And it's very important for the experimentalists to assess all the systematic uncertainties really well. And then the game is, when you put together the theory and the experiments in a collider environment, the problem is all the interpretation. So how do we look at the background prediction, the signal, and all the statistics we have to do? So to really declare a kind of discovery or to really see a deviation, we need to collect a lot of these events in these controllable events and definitely say that there is something or there isn't. Okay, so, and again, I think you have already seen that, so I will go quite fast, but I think it's important to give a little bit of recap of what are the kind of colliders that we are looking at. So typically, you have two particles smashing and producing some object into the final state, okay? And we have had different kind of collider, fixed target collider, wherever the target is still at the beginning and then is hit by some object. And again, if you look at that, at the kinematics, you see that the mass of the particle that you can produce in the final state grows like the square root of the energy of the collision. So it goes definitely less fast than it grows in a circular collider whenever you have two particles that are smashing against each other and they go in opposite direction. However, you can have denser targets, so you have larger collision rate. Whenever you smash something, if you have more stuff in your target, you can definitely have more collision per, so more events per collision. So I think at the moment, the focus is really on circular collider, but we had, and whenever we will look at what data we use to understand the structure of the proton, we are using both kind of experiments. So that's why I wanted to mention it. Okay, and here it's the list for your reference of all the colliders that has led us to a deeper understanding of the standard model interaction and the structure of the protons. So these are the ones that have been worked in the past and are no longer functioning. We had the electron and proton and positron collider, PP bar collider. The last one was a tevatron, from which we had a lot of very important information. And now here we have the colliders that are currently working, Babar and Bell, LHC, EIC. And then depending on the outcome of what's happening here, there are different planning in the community that have to be approved. So we really stand on the shoulder of giants because we have lots of experimental information that came from the collider before, and I'm going to mention some of them and what we learned from each of them. And we have really a wealth of opportunity from the things that we can look at from different points of view. And I will focus on the Large Hadron Collider and on the EIC, how they can give complementary information about the proton structure at the end. Okay, very good. So let's start from high energy and see what we need, and then we go at the basics. So from high energy, it's very exciting, at least for me personally, because I started to do physics when the LHC was starting. So it's really nice because somehow my whole career and understanding of things went through, the start of the data taking at this most powerful accelerator that was ever built. And it really proved to be extremely successful in run 1 and run 2. And now we are having the third run, and we have approved the run of the LHC for the next 25 years. So there is really a wealth of information that has already come out of it and will come out of it even more. And as you can see, in terms of what we can produce at the LHC, in terms of reach, so what are the final states that we can produce when we smash protons against protons at the LHC, you can see that thanks to the upgrade that will be done at the LHC in the next 5 years, now we can really reach masses we will reach masses up to 5 TeV, okay? So, and again, to do that, we have different parton channel, I will show you later, that will contribute to that. So we can really, thanks to the increase in the luminosity, so the number of events that we can observe at every smashing of the 2 protons, we can really probe final states that are up to 5 TeV, so something that was never explored before, okay? And the other thing that, again, I will connect to the structure of the proton later on, is that the discovery of the Higgs was clearly one of the greatest things that happened in 2012. And now we are kind of, every run of the LHC, we are rediscovering the Higgs. So we are seeing the same bump, and we are observing more and more properties of this new particle that was observed only 10 years ago. And we are trying to sift through the data all the properties of this particle that is discovered. Okay, very good. So really, the LHC is at the forefront of the exploration of especially the high energy regime. And it's a key. So whatever we are going to find or not find is the key to plan for future colliders that go into the high energy direction. So exploring higher and higher final states and masses. And clearly, precise predictions are the key not to miss this unique opportunity. So then I will quantify, before entering into the details, what is the precision that we really need. And what are the limiting factors in observing things at the precision that we would like, okay? So at the beginning, I have to say that in 2006, whenever there were the first prediction of, what are we gonna see with the LHC, people were not imagining that precision physics was something possible at the Hadron Collider, because whenever you have 2 protons smashing against each other, you really have a messy final state, because as I'm going to show you, from electron and positron, you have a very clean signal in the final state. Whenever you have proton-proton, you have a lot of QCD radiation, lot of particles coming out of every collision. So it was not meant to be a kind of precision environment. It was meant to reach higher energy because we have larger mass initial state. However, the great experimental performance really pushed us to the point where theory was not expecting that they had to go so precise to match the precision of the experiments, okay? Because we had a lot of statistics and good control of the systematics of the experiments. So if you can see here, these are the experimental measures for some of the cross-sections that we really want to verify in the standard models. For example, proton-proton into the W boson, proton-proton into the Z, or photon, proton-proton into TT bar, or proton-proton into a single top, or into Higgs, or into a pair of W. So each of these is a different cross-section, and this is the precision that has been achieved at the LHC in the measurement. So as you can see, these are the points for the 7 TeV run, this is for the 8 TeV run, and this is for the 13 TeV run. As you can see, the precision, the experimental precision is incredibly small. So the line that you might see or might not see here are really, really tiny. And they are sometimes tinier than the gray line, which is our experimental prediction, okay? And then I will tell you how we calculate this gray line. So what is the uncertainty associated to each of the theoretical prediction points that you see here. But as you can see, we are really competing. So theorists are competing with the experimentalists in order to really get better. So there is this healthy competition between the experimental measurement and theoretical predictions. And I have to say that people were not expecting to reach this level of precision. And as you can see, the other thing is how good agreement we have for this kind of cross-section between the theoretical predictions, which are the gray line, and the experimental measurement. So there is no spectacular deviations, nothing. You know, we really see that what has been predicted to an incredible accuracy is actually what has been observed so far, okay? And here we have a bit more processes. And again, it's just everything is normalized to the theory. So the theoretical predictions are again in gray, and these are the various measurements. Here you can see that, you know, beyond the states that I showed you before, there is a bit of more room for deviation, because again, whenever you look at gamma production, you see that it's all right. So it's within the 1 sigma uncertainty. And you can see here how the theoretical prediction is worse than the experimental the theoretical accuracy is worse than the experimental one. And also for the W, Z, TT bar. But when we go to states that are more complicated, for example, these TT bar and W, you can see that this is the prediction at 13 TV, this is the prediction at 8 TV, and at, what is it? Yes. And you can see that the theoretical prediction is here. This is the experimental measurement. So there is a bit of deviation. So nothing spectacular, because, you know, these are the 2 sigma. So 95% confidence level, you can still, there is an overlap if you take the 99% confidence level. So that, you know, you see that there is room for some deviations. But again, or for example, when you look at W, gamma, gamma, it's a 2 sigma deviation from the standard model. So as you can see, but these are all things that as we get more data from the LHC, these bands are going to shrink. So it's important that there is a good control on the theoretical prediction, because, you know, if they shrink and remain in the same place, we have seen a deviation, okay? If they shrink and the theoretical prediction moves, we haven't seen it. So it's really important. So when you look at it, I think it's impressive, the level that we are getting to. But you also see that there is a lot of work to be done, okay? So both from the theorist point of view and from the experimentalist point of view. Any questions about that? This is our standard model prediction. So the theory here is standard model theory. And you can see, I think these predictions here are at the best accuracy we have. Best accuracy means the highest perturbative orders that people have computed in QCD, with electroweak corrections that have been added on top of it, and using the best Parton distribution functions that have been agreed to use by the experimentalists. So if there is any new physics, this will shift the predictions either in the direction of the data or in the opposite direction, okay? And I'm gonna show some predictions for models beyond the standard one in the last lecture, okay? Just to see what is the exclusion limit. So far we only have exclusion limits, okay? Any other questions about that? It's very dense in a sense, this slide, because there are so many processes. And behind each of these gray line, it looks dumb, but, you know, there's so much work, the work of so many graduate students and postdocs and staff members, you know, really. Sometimes to go from one order to the next, it took 20 years to do the calculation to go to the next perturbative order. So I think whenever one looks at a plot like this, so they're always flashed upon us whenever we go to conferences. But if you think of the human input that there is in each of those, I think it's quite impressive. Anyway. Okay, very good. So now let's look at the big picture. So what do we want to do? So we want to compare tons of these pictures. So this is a kind of a simulation of a real event by CMS, which is one of the detector that we have at the LHC, to the prediction. So as I say, it looks like a mess, no? So these are a bunch of protons smashing against the other, and they take billions of pictures like that every second, okay? So, and what do you see here? So these 2 lines here, I hope not to make any mistakes. So you've got the red line that is a muon, because this has been taken a picture of in the outer layer of your detector that can see muon. So they do a reconstruction and they see that the muon came out of the collision spot here in the middle of the detector. Then they see these 2 green lines, and they see that these 2 are 2 electrons, because these are seen in the second outer layer, which is the one where there is a electron calorimeter. And these two here, I think these are two jets, so like collimated bunch of hadrons that come out of the detector in the same direction and that deposit enough energy into the hadronic calorimeter. So the point here is, okay, they see that, how do they compare to theoretical predictions, okay? So in particular here, this event, they say this is a proton-proton that decayed into a top quark, so that produce a top quark and a Z quark plus, sorry, a top quark, a Z boson, and another light quark, which hadronized, and the top decay into a bottom and a W, the W decay into a muon and the neutrino, and the Z decayed into a E plus E minus. Okay, so this is a really complicated thing. So in a sense, even to reconstruct what actually happened, so what is the kind of theory box to compare these two, you have to do a lot of reconstruction of what you have seen and go back to what happened at the Parton model, okay? So how do we picture this event from a theorist point of view? So this is our theoretical picture that you normally have. I don't know which one is nicer. I think the experimentalists win, I think, but whatever. I think this shows that lots of things happening. So let me guide you through that. So these are the two protons that come in. And as you can see, these are not elementary particles. They are made of other stuff they have inside, okay? So these green boxes are the proton, and I circled them in pink. Then here is where the main collision happens, is, you know, so out of the protons, you get like the main partons that are the ones that smash against each other to produce a final state. And these are these two here. So you get the gluon out of one of the proton and a quark out of the other proton. By the time they reach the point of collision, they radiate stuff. So they lose other quark, they lose other gluon, because, you know, QCD keeps happening. So you keep having interactions. So what really gets to the collision point are two gluons, okay? Because the quark in the meantime became a gluon, okay? And then out of it, you get these two objects. Actually, in this case, you have 4 objects that come out. So you have a quark here, another quark, a gluon, and a Higgs, okay? Good. So this is what happened at the level of the collision. This is what you use the hard scattering of partons, and you use perturbative QCD to calculate the amplitude for gluon, gluon going into quark, quark, gluon, Higgs, okay? Whatever. And then on top of it, lots of other things happening, because, you know, you don't see a quark, you don't see a gluon, you don't see a Higgs. You see the things that these guys decay into by the time they reach the detectors. And this is all this mess you see around here. So there is all the parton showering. So each of the things that comes out of the collision showers into something else. And then eventually they hadronize into hadrons that are then seen by the detectors, okay? So you think, come on. And the other mess is this, okay? So that on top of the proton that actually participate to the hard collision, there are the spectator parts. So on top of the partons that participate to the collision, there are the spectator partons over here that do some mess as well. They interact with each other and they create other soft things that come out. So when you look at this picture, you think, how possibly can we get any precision in an environment like that? So how can we possibly get 1% accuracy, just 1% or 2% error in our theoretical predictions? The key of that is factorization theorem. So it's the fact that we can really divide. So the Romans said divide et impera, so split and rule. So that's what we do here. We split this picture into 4 boxes that we kind of know how to deal with. And then we put them together with a kind of factorization. So we factorize everything that happens into 4 bits that we can manage, okay, that we can use different techniques to calculate. So the 4 bits are the hard scattering here. So everything that happens when the two partons, the two main partons that come out of the proton collide. And this is what we need. Perturbative QCD, perturbative electroweak theory to calculate a number. So the cross-section that you have seen in your QFT courses or anything is what you compute out of this box, okay? And this is something that we have to use perturbative techniques in order to calculate. Then we have the second boxes, which is this thing, which is the structure of the proton. So how we parameterize this by telling you what is the probability that at a given energy, when I smash two protons at a given energy, a given parton A and a given parton B come out of the proton and interact, okay, with each other into this green box. And again, this is something that fortunately factorizes. So everything that has to do with the proton structure is independent of what happens in this box. And this is what we will learn by the end of this lecture. And then we have all this yellow stuff, which is the parton showering and hadronization, and that again, we can compute thanks to perturbative techniques, but not the usual expansion. We have a different kind of expansion. I don't have time to talk about it, but there are lots of people working on this bit. And these are also stuff that somehow, fortunately, are small corrections to most of the things that we observe, okay? But people know how to deal with that. And then this is the multiple parton interaction underlying events that people usually model in a non-perturbative way. But again, this is a small correction for the processes that I showed before. So let's see this picturing in a kind of more mathematical form, because that's what I'm gonna use. So, and this is what we will understand by the end of these two lectures. So collinear factorization, so the cross-section for proton-proton going into some stuff that I call AB is equal to the convolution. So it's the integral product of these two functions that are the parton distribution functions of proton 1 and proton B that collide against each other times sigma hat, the partonic cross-section for parton I, parton J going into AB, okay? Plus everything else you can put in these correction terms, that is things that have to do with the soft stuff, higher twist, parton shower, multiple interactions, okay? So I'm gonna talk about these two things in turn. So first, let's start with the partonic cross-section, which is what we compute using perturbative QCD and electroweak corrections. And then I will talk about the PDFs. And then we go at the origin of this formula, okay? But let me first tell you how we know these bits now. Okay, very good. So let's look at each bit in turn. So let me just start with the perturbative expansion. Again, I'm sure you have seen this in different sources during the lectures here, so I don't want to spend too much time, but I just want to talk about if you want, the easiest example of perturbative expansion that you can think of, that is the one that proved, if you want, the existence of the gluons, okay? So this is the ratio of E plus E minus going into hadrons and E plus E minus going into muons, okay? So it's the ratio of what happens whenever you have here Q bar or mu plus mu minus at the parton level, okay? Very good. So if you just consider the leading order, so the three-level diagram, if you just consider that, okay? So the ratio is very simple because the only difference is, so the ratio is just given by the number of colors, so 3 colors you've got in QCD, and then the sum over I of the charges of the quarks that you can produce in the final state, because from the point of view of the interaction, the only difference here is the QED interaction between the photon, if you want, and the quarks. Okay, then whenever you start adding the first order QCD correction, so to this diagram, you need to add virtual correction, so to the numerator, right? Because you don't have QCD interaction for the muon. So in the numerator, you have to add virtual exchange of gluons between the two quarks and real emission from either legs, so from quark 1 or quark 2. Whenever you do that, you can see that this is beautiful because so in each of these diagrams separately, you have a singularity. I don't know did you ever compute these diagrams? Exactly. So you see that you have a 1 over epsilon. Yes. Yeah, we are ignoring QED. So let's just do QCD, which is, if you want, QCD has a coupling that is 10 times larger than QED, so we can ignore it, okay, in the first order. Of course, if we want to do electroweak correction, we need to consider the initial state radiation and the final state radiation. But let's just focus on QCD, okay? So here you have a singularity, and a singularity here, but I think you must have seen it in the lecture that the two cancel beautifully. And so the only here you have the same as the ratio at the leading order plus a correction which is proportional to alpha S. So the strong coupling constant divided by pi, okay? What happens if you go to the next order? Again, you must have seen it. When you go to the second order in QCD, then you start having different corrections. So you have this, when you consider the virtual square, then you have virtual and real. And then you have two real emission, and then you have another diagram like this, so emission from out of a loop, whatever. So it gets complicated more because of the kind of self-interacting nature of QCD. You have lots of stuff happening, okay? And what happens here? Here, you see that whenever you compute this diagram, you have the term that we computed before, plus you have another term that has this structure. So it's alpha S squared, so 2 powers of the strong coupling constant. Then you have some constant, and then you have plus. So if you use a cutoff regularization, like you have a log of the cutoff square divided by the square of, by Q, which is the energy of the interaction you have, okay? So clearly you have a UV, ultraviolet divergence, because it's proportional to the log of the cutoff that you put in the UV region. So it diverges when you integrate the loop integral over really, really high energy. That doesn't cancel. But how do you deal with that? You know really well, you have to do a renormalization procedure to absorb the UV divergence into a redefinition of the strong coupling constant, okay? So basically you say that your real strong coupling constant is the bare coupling constant, which can also be infinite, okay? Which is infinite, which absorb this UV divergence order by order, okay? And in this way, when you do this procedure, you see that the strong coupling constant is no longer something that you measure and it's the same at all energies, but it takes a dependence on what we call the renormalization scale mu, okay? So that's the process that I'm sure you're familiar with, but I wanted to remind you because the same thing with a different kind of divergences will happen for the Parton distribution functions, okay? So UV divergence reabsorbed into the running of the strong coupling constant, okay? So from here, if you ask that this doesn't depend on the scale, you get the renormalization group equation for the strong coupling constant, which is this thing. That this is at the first order, so you get only this coefficient B0 in front of it. If you go to higher order, and actually this has been computed up to 5 loops, I think, you can really have the running of the strong coupling constant to a really, really incredible precision in QCD. And the beautiful thing, which is the one related with the confinement, is that because you have the self-coupling of the gluon with themselves, because it's a non-abelian gauge theory, the quark loop diagram contributes with NF negative terms, while the quark loop diagram gives a positive contribution. And when you put the two contributions from the gluon self-interaction with the contribution of the quarks together, you get that the beta function is negative in QCD, which means that in QCD, the coupling decreases with the scale, okay? And that's important for what we are gonna say later on. So you have the Landau pole, which is the energy below which QCD is no longer perturbative, and above the Landau pole, you get a perturbative expansion that gets better and better as you go to larger values of the scale. This is the opposite of what happens in QED. In QED, instead, you have that the alpha E, the electromagnetic coupling, increases with the scale, okay? So that's something that as you go to larger scale, you have a larger value of the electromagnetic coupling, okay? But this scale is far above even the Planck scale. So it's nothing that we ever worry about because we always are in the perturbative regime with QED, okay? Any questions about that? Okay, I'm sure you have already seen it. And it's important because really the strong coupling constant, every theoretical prediction we have is expressed in terms of the renormalized coupling alpha S of mu r as a function of this unphysical renormalization scale. So whenever we were talking about the partonic cross-section of parton I, parton J going to AB, we always have an expansion in alpha S, okay? At a given scale, which we usually set to the scale of the physical interaction. Very good. And okay, different processes starts at different K naught. For example, whenever we have a Z production, there is no alpha S, no strong coupling at the leading order because this is a QED coupling. If you instead look at, for example, jet production, you have two gluon going into two quark, you have alpha S. You have already power of 2 at the 3 level, okay? So K naught depends on the process you're looking at. And that's something I already said. Okay, very good. So the strong coupling constant is the only 3 parameters in the QCD Lagrangian besides the quark masses. And as you can see here, there is a huge wealth of measurement. So it's not, so what people measure is something that they measure a process at a given energy that you can see here, and they compare the fit of the alpha at that scale. So they compare alpha at the scale Q of the measurement to the strong coupling constant, which is this prediction you've got over here. And you see there is a perfect agreement, okay? And again, I just want to make a parallel with what we're going to say later on. So let's take one of these measurements that you always see on the PDG. No? So this is really the measurement of the strong coupling constant at different values of the scale. For example, let's take this pink one, which is PP top. So how is this pink line here extracted? Okay, so this is alpha S calculated at the scale of 172 GeV. And this is the measurement we have. So what people do here is they look at the agreement between the data for, so the data in this case is proton into top anti-top, and the top decays into something else, into W and bottom, and the W decays on turn. So they look at the agreement between the data and the theory predictions computed at different values of alpha S, okay? And they basically get a parabola, and which is, because you see, data minus theory square, it depends quadratically on alpha S, okay? So that's a nice parabola, and they see where they have the minimum of the parabola and what is the error on delta K square equal to 1, okay? It's the usual statistics you do. So this is an example of the extraction of a parameter, which is in this case is alpha S at the mass of the TT bar per production from the fit of the data. So we will see something, we will go a lot into this parabola kind of thing tomorrow, but I just wanted to give you an example that you don't do it only for the parton distribution function of the proton, you also do it for alpha S, okay? So each of these points, usually you do something like that, okay? Very good. So any questions about that? Okay, so I have to go a bit faster. So now we have alpha S, and then I just wanted to give you a concept on the partonic cross-section, giving you an example about the Higgs cross-section, because we will need it for later. And so imagine you have a partonic cross-section with 2 particles that go into 2 particles. And to illustrate the concept, I just draw some lines, okay? We don't care about what the particles are just lines with the interaction. So as I said before, at the 3 level, you only have 2 into 2. So it's just this diagram. When you go to next to leading order, you need to look at real emission, like this case. So you take the square of the 2 to 3, and then you have the 1 loop diagram and the interference with the 3 level, okay? And then when you go to next leading order, you have the 3 level, which is 2 to 4. So it goes higher in complexity. Then you have the 1 loop with 2 to 3 times So the one loop times the 2 to 3, then you have the 2 loops here times the 3 level, and then you have the 1 loop square. So you have much more ingredients that enter the computation. Any questions about that? Yeah? Okay, so anyway, just to say that you have much more stuff to calculate when you go higher. And how do we know if this kind of expansion, so we are doing an expansion in the couplings, okay? Because every time we go from leading to next to leading to next to next to leading, we add one coupling, and we are doing a perturbative expansion about that. How do we know that it's working? So I want to give you an example of proton-proton into Higgs via gluon-gluon fusion. So it's the channel that produces most Higgs. So the Higgs boson is mostly produced at the LHC via this process, which is gluon-gluon into Higgs. And you can see here that this is one of the few partonic cross-section that is not a next cube leading order, so even one order higher than that, okay? So there are 5 processes that are known as next cube leading order. And this is a nice example because we see that the perturbative series does not converge well until we go to next cube leading order, okay? While the other processes work well, this is the counterexample. So that is really one of the processes for which you really need to do really the hard work of going to next cube leading order before seeing that the series converges. So these are the coefficients that, so we are at 13 TeV, and these are the numbers we get for the order. So you can see that this is the 3-level cross-section, 961 picobarn, which is already order alpha S cube because I didn't draw it, sorry about that. So you have, this is the leading order diagram, okay? Gluon-gluon, a top loop, and then the Higgs, okay? So this is the diagram, and people can simplify it like that. So you can have an effective interaction that kind of smashes. So you send the mass of the top to infinity, and this becomes a vertex in the gluon effective filter. It doesn't matter. So you can say that this loop, you can squash it into a single point, okay? So the leading order diagram is already alpha S squared, okay? And then on top of it, you add all the corrections. Okay, very good. And you can see here that the coefficients become larger as you go to higher order, which is not what you normally expect. And we can see already from the coefficient why this thing is not working well. But let's look at it a bit more in details. So we saw this series, again, whenever you write alpha S, because alpha S, we said, is not a fixed quantity, but it depends on the scale at which you're looking at. In this case, this number are calculated with alpha S calculated at the mass of the Higgs divided by 2. So 130 divided by 2, it's, help me, 65 GeV, okay? So this is alpha S at 65 GeV, okay? Very good. So how do we know what is, so let's say I am lazy, I just want to compute the first order in this expansion. How do I know what is the uncertainty associated with this order? Okay, because I know that I only computed the first order, but there are more that I should calculate. Okay, so what is the theoretical uncertainty if I stop my calculation at leading order? How do you compute it? Do you have an idea? What do people do normally? How can I give the experimentalist what is an assessment of the uncertainty that I do in truncating the series to the first coefficient? That's an important problem, no? Because I give a number, but I know that this number is not the full story. How do I estimate what are the possible contributions that come from the next numbers that I'm not computing? How would you do? Or do you know what they do in phenomenology? No? Anybody has an idea? What would you do? You're a theorist. How many of you are theorists? 1, 2, 3, 4, 5. Okay, good. You're a theorist. You want to give an uncertainty associated with your prediction, right? Yes or no? Yeah. How do you do here? Exactly. I want to give the error. Yes. I want to give the error associated with the truncation of the series to this order. But it's not an easy problem, because I'm telling you that already now people are really debating, because we have a kind of half-baked solution that has been used for decades, but now people are thinking maybe it's not the best way. And this is the example why. So what do people do? They say, okay, because alpha s, I computed it at a random value of the scale, which is mx divided by 2. Let me vary the scale in alpha s and see how the number I'm giving you changes as I vary the renormalization scale at which I compute alpha s. So when alpha s is computed at mu equal to mu naught, okay? This is the central number I gave you before. I don't know why it's different. Okay, let's say it's 12 in some unit, okay? No, it's 16. Good, but now I vary the scale by a factor of 2. So I vary the renormalization scale up by a factor of 2. So I compute the cross-section at alpha s equal to mass of the Higgs, and I get this number. And then I compute the cross-section with the renormalization scale set at mass of the Higgs divided by 4. And this is the number. And I take this as the estimate of the uncertainty of my prediction. Why? It's because if you vary the scale and you put it into a renormalization group equation, you get these terms that are of higher order. So you say, if I change this scale by a factor of 2, I'm picking up the contribution of some alpha cube terms, which are next in terms of the perturbative expansion, that appear just from the running of alpha s. So what I'm thinking is that if these terms capture what's the next order, then I'm gonna be fine. So this is the thing. But then people say, okay, let's do the job and compute the next leading order prediction. It's this green line. You see why it doesn't work? Can you see, looking at this picture, why it doesn't work? Because you remember before I said, I tell you this number and I can tell you that my error is somewhere between here and here. So the cross-section will be between, I don't know, 18 and 12 if you compute the next order. Then you compute the next order and you are, it's too far away. It's super far away. So, and then you say, all right, now I vary again by a factor of 2, and you see that the error on the next order is larger than the error you had on the leading order, which again is counterintuitive, okay? I'm not saying that everything works this way. I don't want to give you a cynical approach to perturbation theory, but this is what happens in this case, okay? And then you do the same on next to leading. And again, it's not beautiful because you can see that the next to leading, it was between here and here, and the next to next is above the upper range that I gave for the next to leading order, okay? And we start reaching convergence only on next cube leading order. So finally, it's only when you go to the third order, so alpha s to the fifth in your 3-level cross-section, that you reach a good perturbative convergence. Okay, so what we learned from here, we learned that the estimate of the theory uncertainty, so is done, so the missing higher order uncertainty is estimated by change of the cross-section value when we vary the renormalization scale by a factor of 2. So here I simplified it because I only vary the renormalization scale. I can tell you that you have to vary another scale, but it doesn't matter. I'll tell you about it later, but the picture doesn't change. Because when you really vary them all together, you see that the leading order prediction is here, the next to leading is far above, the next to next here, and next cube is there. Yes? Yeah, why the factor of 2? That's a very good question. In fact, it's just a recipe, yeah? It's because the problem is you do, so it's just a convention, but why should you take 2? It's just what people agreed on. I don't know. You can take a factor of 3, of course. There is nothing mystical in the factor of 2, you know, you can, but the problem is that if you do a factor of 3, then the theoretical uncertainty of any prediction increases by a lot, no? So So now people are thinking about Bayesian methods, so this is a very active field of research, because before, when we were here, okay, you say, yeah, leading order, next leading, fine. But then the fact that when we go to higher order and it doesn't converge well, then people are thinking, is there any other way, like based on, for example, on the expectation of the perturbative series converging? So is there a kind of Bayesian approach to do that? But this is still a very active field of research, okay? Good. I think just to say that this is one component of the cross-section, okay, so of the theoretical uncertainty of the cross-section. Here, how far are we? So you can see here an NNLO status of the calculation. So basically, in 2005, so the only processes were known up to 15 years ago were Higgs and W and Z up to next leading order. And now, as you can see, there have been a proliferation of calculation and next leading order for all these processes you see here. And clearly, the more legs you have in a process, so for example, if you have W, Higgs, and Z, you already start with 3 particles in the final state, so it becomes really a mess to do a next leading order calculation. So it took 20 years to go from next to leading to next to leading. And now there are 5 processes that have been calculated in the past 2 years to next cube leading order. So Higgs gluon fusion, Higgs via vector boson fusion, BB bar into Higgs, and W and Z production. Okay, so these are the ones that are really the frontier. Now we know them are next cube leading order. And actually the W and Z, I will tell you in the last lecture if I have time. It's interesting because there was a wonderful perturbative convergence up to next leading order. And now with the next cube is outside the error band of the next leading order. So again, this is telling us that we have to have a bit better estimate of this uncertainty. Okay, do I have 5 minutes? Yeah, 5 minutes. Okay, so we talked about this bit, okay? So the partonic cross-section. Now I want to tell you, just as an introduction, about the Parton distribution functions, which we will focus on for other 4 hours, so don't worry. But I just want to give you a kind of what uncertainty do we associate with this function. So I told you about the uncertainty associated with the green bit. Now let's talk about the pink bit. So PDF uncertainty. So let's look again at, let's go here, it doesn't matter. So this is 2016 update. So this is gluon fusion into Higgs, okay? Which is the largest cross-section for the Higgs. And this is the component of the uncertainty that we saw before, is the red one. So at next cube leading order, we have 4% uncertainty due to missing higher orders, okay? So what we still don't know, the next to 4th leading order things that we haven't calculated. And then there is another uncertainty, which is the blue one, which is the one associated with the Parton distribution functions, okay? So whenever I'm giving a number to the experimentalist, I have to tell them, I know that to our best knowledge of the standard model, the production cross-section for the Higgs via gluon fusion is 48.5 picobarn plus a 7% uncertainty, half of which comes from the lack of knowledge of the higher order in perturbative QCD, and half of which comes from our imperfect knowledge of the structure of the proton, okay? So you have to give a kind of balance of the uncertainty. For the vector boson fusion, so this process, so you have 2 quarks, they emit a W or a Z, and they go into a gluon, which is the second largest cross-section for the Higgs at the LHC. The cross-section is 3.78 picobarn. You see that the dominant uncertainty is the one on the structure of the proton, the blue one, because already at our next leading order, which, okay, I haven't updated, it's very small, the uncertainty, okay? And so on. So I think one reason why we want to improve our understanding of the proton structure is because we want to reduce the blue bars, okay? So if you want to be precise, we have to reduce the size of the blue bars. Otherwise, the uncertainties for our predictions are not going to decrease, okay? It's not enough to reduce the red component by going to higher orders. Another reason is because whenever you want to extract quantities, like for example, the W mass from the data, the LHC, again, they do some kind of fit like the one I was showing you before for alpha S, but it's a much more complicated game. And they have several systematics that come out of, that's an old, but okay, that come from uncertainties. And the dominant one at the LHC is the uncertainty and the structure of the proton. So this is the kind of bottleneck in the determination of the W mass from the LHC via parameter extraction, because the PDF represents a large component of the uncertainty. So it's a kind of systematic uncertainty that prevents us from knowing precisely the parameters we want to extract at the LHC. The other thing, again, this is an old plot, but imagine we produce gluinos that are 2 TeV. So 2 gluinos that you have a final state of 4 TeV. I will show you tomorrow why, when you go to produce heavy object, you need to know the structure of the proton in a given region, and we know it really badly. So the uncertainty and the production of this particle is basically 200% because we don't know the structure of the proton in the large X region. So if we want to make precise prediction for new physics, new heavy particle production, we need to get better in these uncertainties that you can see here, okay? I'll tell you more later. And finally, that's something really dear to my heart because I'm doing a lot of research about it. So before, the structure of the proton was not a line with an error band, it was just a line, okay? So people were saying, okay, this is my best central prediction for having a quark that carries a fraction X of the proton. And in 1995, so they had these lines computed by various people, and the data were overshooting the theoretical prediction that you got using these particle distribution functions, okay? So there were tons of papers about new physics and lots of, contact interaction. We discover extra dimension, we discover something. So this happened at the Tevatron in 1995. But the only reason for this discrepancy is because at that time, there was no information on the particle distribution function and the uncertainty by which we didn't know them in one region. Yes. Yeah, it was a measurement of jets in the final state. So in particular, again, whenever you have, like, for example, two quarks in the final state, they kind of hadronize, okay? And the jet transverse energy has to do with the energy that they deposit in the calorimeters times the cosine of the angle that they reach the calorimeter, something like that, okay? So it's really a measurement of the jets. And as you can see, the data were completely off the theoretical predictions. So these were the theoretical predictions and these were the data. And there was something increasing with the scale. So it looked like new physics and people were very excited about it. But then people who do the fit of the structure of the proton put this data into the fit and the discrepancy disappeared. So you see now the prediction was going back to agree with the standard model, okay? So I think this is telling us that whenever the discrepancy was just a lack of knowledge of the structure of the proton, they had nothing to do with new physics. It was just because we didn't know the proton at that X fraction, okay? So it's very important to estimate what is the blue uncertainty that I showed you before. Otherwise, we might see new physics where it's not there. So, and I will tell you more. I think now we risk the other way around. So we risk of absorbing new physics in our fits of the PDFs. So, but that's something I will tell you in the last lecture. But I think it's a very interesting if you want philosophical problem as well. And okay, that's it. I think that's a good end of the first part of the lecture. And then we go to the Parton model after the break. Okay, thank you very much.